Get this, Teflon. You know, that stuff that keeps your eggs from sticking to the pan?
Yeah.
It's actually 10 to the power of 30 times more resistant to electricity than copper.
Wow.
It's mind-blowing, right? That's like comparing a snail's pace to, I don't know, a spaceship going at warp speed.
That's a huge difference.
It is, yeah.
Yeah.
But speaking of shocking differences, welcome back to the channel, everyone. Today we're diving into a topic that powers our world. Electrical resistance.
Resistance is everywhere, isn't it?
It is, and it's way more interesting than it might sound at first. We're going to unpack everything from the basics of ohms to the real-world applications you see every single day.
You encounter it constantly without even realizing it.
Exactly. Think of us as your AI guides to the electrifying world of resistance. So let's start with the basics. When we talk about electrical resistance, what exactly are we talking about?
Okay, so imagine trying to push, let's say, a whole crowd of people through a narrow doorway.
Okay, I can picture that. It'd be pretty tough.
It would be, right. The more people you try to squeeze through, the harder it gets. That's essentially what resistance is.
So more resistance, harder for things to flow through.
Exactly. It's a measure of how much a material opposes the flow of electric current.
Electric current, those tiny charged particles, electrons, right?
Right. The electrons are trying to flow through the material, and resistance is what's slowing them down.
So I guess if you had a wider doorway, it'd be easier for the crowd to pass through.
Exactly. And just like a wider doorway, a material with low resistance allows current to flow much more freely.
So if resistance is how much something opposes the flow, then the opposite would be how easily it flows.
You got it. That's called conductance.
Conductance.
High conductance means low resistance, and vice versa.
Two sides of the same coin. Now, I've always heard about Ohm's law, but could you give us a little refresher on how it all fits into this?
Ohm's law, that's the key to understanding how voltage, current, and resistance all relate to each other.
Right, and maybe just a quick reminder, what are voltage and current again?
Okay, think of voltage as the pressure pushing those electrons through a circuit.
Okay, kind of like the force that makes water flow through a pipe.
Exactly. The higher the voltage, the stronger the push. Current, on the other hand, is the actual flow of electrons, the amount of charge passing a point each second.
So higher voltage, stronger push, higher current, more flow.
You got it. And Ohm's law neatly ties them together, saying that resistance is equal to voltage divided by current.
Meaning if you increase the voltage, keeping resistance the same, the current will also increase proportionally.
You've got it. It's a beautifully direct relationship.
Now, does this apply to every single material out there? Do they all behave the same way?
Good question. Materials that strictly follow Ohm's law, we call them ohmic material. Their resistance stays pretty constant. Their voltage current graph would be a straight line.
Straightforward, but what about the materials that don't play by Ohm's law?
Yes, those are the non-ohmic materials.
Oh, no.
Their resistance can change depending on the voltage or current.
Oh, interesting. What are some examples of those?
Think about diodes, fluorescent lamps. Their relationship between voltage and current is a bit more complex.
More complex, got it.
Yeah.
So let's talk about what actually determines a material's resistance in the first place. What makes something have high resistance or low resistance?
One of the biggest things is the type of material itself.
Makes sense? Different materials are different.
Different materials have different atomic structures, and that directly affects how easily those electrons can move through them.
Okay, so for example, copper is a good conductor because it has a bunch of free electrons that can carry that current easily.
Absolutely. Metals in general have low resistance because of those free electrons. Then you have insulators like rubber or glass. They hold on to their electrons tightly. Their electrons are bound to their atoms, making it really hard for current to flow through. That's why they have high resistance.
So basically it's about how freely those electrons can move.
Precisely.
Does the shape and size of the material also affect resistance? Like, I imagine a long wire would have more resistance than a short one, right?
Absolutely, you're spot on. Longer wire, higher resistance. Thicker wire, lower resistance.
Okay, that's kind of intuitive, right?
Think about a water hose. The longer the hose, the harder it is to push water through.
Oh yeah, makes sense.
Wider hose, easier flow. Same principle applies to electrons.
So we've got the type of material and the size and shape of the material, but how do we actually measure this effect?
That's where resistivity comes in.
Resistivity.
It's like a material's fingerprint when it comes to resistance.
For fingerprint.
It's a property that's unique to each material, no matter its size or shape.
Oh, I see. So resistivity is telling us how much a material inherently resists the flow of current, regardless of whether it's a long wire or a short wire.
Exactly. And of course, the flip side of resistivity is conductivity.
Conductivity, which we talked about earlier, how easily the current flows.
High conductivity equals low resistivity, the opposite.
Right. They're always linked. Is there a way to actually connect resistivity to the resistance of, let's say, a specific piece of wire?
There's a formula. Resistance of a conductor equals its resistivity multiplied by its length, and then you divide that by its cross-sectional area.
So a longer wire with a smaller cross-section will have higher resistance, even if it's made of the same material as a shorter, thicker wire.
Exactly. It all comes down to how easily those electrons can flow through.
Makes sense. Now, we've been talking about direct current this whole time, but what happens when we're dealing with alternating current, AC?
I see. That's where things get a bit more interesting. We have to consider not just resistance, but also something called reactance.
Reactance, that's a new one.
Reactance comes from components like capacitors and inductors.
Capacitors and inductors.
These components can store and release energy, which affects the flow of alternating current in a way that simple resistors don't.
Okay, so it's adding a whole new layer of complexity.
It is.
Is there a way to account for both resistance and reactance in AC circuits?
There is. We use this concept called
Impedance.
It's a broader term that includes both resistance and reactance. It's the total opposition to current flow in an AC circuit.
Impedance, got it. So it's like the big boss of resistance in AC.
You could say that. And just to add another layer, in AC circuits, resistance can actually change depending on the frequency of the alternating current.
Oh, wow. So the frequency also matters.
It does because of things like the skin effect, where the current tends to crowd towards the surface of a conductor at higher frequencies.
So AC circuits are a whole different ballgame when it comes to resistance.
They are, but understanding these fundamentals will give you a good foundation.
Okay, great. I think we've covered a lot on the concept of resistance itself, but I'm curious about real-world examples. Where does this actually show up in our everyday lives?
One of the most common applications is in generating heat.
Heat?
Yeah, when current flows through a resistor, some of that electrical energy gets converted into heat. We call it joule heating.
Joule heating. So is that how things like electric heaters and toasters work?
Exactly. Those appliances, hair dryers, incandescent light bulbs, they all use joule heating.
Wow, so it's a really simple principle with a ton of applications.
It is.
Are there other applications of resistance beyond just generating heat?
Absolutely. Did you know resistance can also be used to sense temperature?
Really? How does that work?
We use things called thermistors. Basically, resistors with a special ability. Their resistance changes very predictably with temperature.
So if you measure the resistance of a thermistor, you can figure out the temperature.
Precisely. They're used in everything from digital thermometers to thermostats that control the temperature in your home.
So resistance is playing a role in keeping our homes comfortable. That's incredible. Any other interesting applications you want to share?
Definitely. Another fascinating one is in strain gauges. These devices use the fact that the resistance of a conductor changes when it's stretched or compressed.
Wait, you're saying by measuring the change in resistance, we can actually measure how much something is being stretched or squeezed?
You got it.
Wow.
Strain gauges are used in tons of things, like measuring the stress on bridges and buildings, even monitoring the pressure in car tires.
So they're essential for safety and reliability. Resistance is way more versatile than I ever imagined.
It really is.
And we've probably only scratched the surface.
Oh, for sure. Speaking of pushing the boundaries, there's another application of resistance that's just mind-blowing. Superconductivity.
Superconductivity. Sounds futuristic, like something out of a sci-fi movie.
Yeah, it kind of is.
Yeah.
Imagine electricity flowing with absolutely zero resistance.
Zero resistance.
That's the world of superconductors. Materials that can carry current forever with no energy loss.
No energy loss. So you're telling me electrons can just zip around with no friction at all?
Exactly. Like they found a loophole in the laws of physics. In normal conductors, you always lose some energy as heat because of resistance.
Yeah, right.
But in a superconductor, that loss just doesn't happen.
That's incredible. What kind of materials can do that?
For a long time, superconductivity was only seen at super low temperatures.
How low are we talking?
Close to absolute zero, like minus 273 degrees Celsius.
Wow, that is cold.
Materials like mercury, lead, certain alloys.
Not exactly everyday stuff.
True, for many years it was mostly in labs. But more recently, there's been a lot of interest in high-temperature superconductors.
High temperature. How high is high temperature?
Well, high is relative. They still need to be cold, but they work at temperatures much higher than those traditional superconductors, something like minus 196 Celsius.
That's the temperature of liquid nitrogen, right?
Exactly.
Still pretty cold, but a lot warmer than absolute zero.
It's a big difference, and using liquid nitrogen is way more practical and cheaper than liquid helium, which is what you'd need for those traditional superconductors.
Right, so it's more accessible.
Exactly. Makes it more feasible for different applications.
So what are some of the potential applications of these high-temperature superconductors?
Oh, the possibilities are huge. Imagine power lines with zero loss, super efficient motors and generators, powerful magnets for things like medical imaging or even levitating trains.
Levitating train.
And lightning-fast computers. We're talking about a whole new level of technology.
It sounds like superconductivity could change the world.
It really could. It's an area that's constantly evolving. Researchers are working on new materials and even more applications all the time.
It's amazing to think that something as basic as electrical resistance could lead to such groundbreaking technology.
It really shows how everything in science is connected. Sometimes the most important discoveries come from understanding and using the simplest things.
Okay, so to sum up, superconductivity, it's like the ultimate victory over resistance, letting electricity flow without any loss. It used to require crazy low temperatures, but high-temperature superconductors are making it more practical. Now, let's shift gears for a minute and talk about something a little closer to home, the role of resistance in signal transmission.
Oh, good point.
Every time we stream videos, listen to music, make a phone call, resistance is there working behind the scenes.
It is. When signals travel through wires, they always run into resistance. And we know resistance converts some of that electrical energy into heat.
So some of the signal strength gets lost along the way.
Right. It's called signal attenuation. The farther the signal travels, the more resistance it meets and the weaker it gets.
That's why we need things like signal boosters for long-distance communication, right?
Exactly. To make up for the loss.
Besides attenuation, does resistance have any other effects on how signals travel?
Well, there's another big one. Noise. Resistance can actually contribute to that unwanted electrical noise in a signal.
Noise, like static on the radio or that crackling you sometimes hear in old recordings?
Exactly. Resistance, especially when you add things like electromagnetic interference, can create these random fluctuations in the signal. That's what we hear as noise.
So higher resistance generally means more noise.
Often, yes. That's why engineers work hard to minimize resistance in circuits and transmission lines.
Right, they want to make sure the signals are clear.
Exactly. They use high-quality materials, carefully design the layout of components, sometimes even use shielding to block out external interference.
It's interesting, resistance is kind of a double-edged sword, isn't it? It's essential for things like heat and controlling current, but it can also cause signal loss and noise.
That's true. It's about finding the right balance. Engineers and scientists are always trying to use resistance to our advantage while minimizing the downsides.
That's what makes this feel so interesting.
Absolutely.
This has been eye-opening. I never realized how much resistance affects our everyday technology. Now I see it everywhere.
That's the power of knowledge. It helps you see the world in a new way.
So we've covered a ton about electrical resistance today, huh?
We have, from those basic ohms to, superconductivity.
It's wild, right? And then all those ways resistance sneaks into our everyday tech.
Really makes you think.
It shows you that even simple ideas can have huge implications.
Totally. And the coolest thing about science?
What's that?
There's always something new to discover. Who knows what we'll find out about resistance in the future?
Right. Maybe we'll have room temperature superconductors.
Imagine that. Or materials with, crazy high conductivity.
That would revolutionize everything.
No.
But before we wrap up this episode, I want to leave our viewers with a little challenge.
A challenge.
Yeah, think about how resistance plays a role in your life.
It's everywhere.
Seriously, look around you. Appliances, your phone, it's all there.
Shaping how we live, work, you name it.
So next time you flip a light switch or stream something, remember resistance is making it happen.
Behind the scenes.
If you found this interesting, hit subscribe and stick around for more deep dives into all things science and tech.
Don't forget to leave your questions in the comments. We love hearing what you're thinking.
And until next time, keep that curiosity burning bright.